Okay, so my screen is visible, right? Yes. Okay, that's fantastic. So let's move on to the Gate Aerospace 2021 question related to jet propulsion. So, as we seen, we have already seen that. So in 2021, there are like relatively large number of problems which is being asked from propulsion. So corely from jet propulsion. So there are like 4 1 mark questions and 5 2 mark questions, totaling about 14 marks from jet propulsion. So let us move on to the questions. The question one is like the combustion process in turboshaft engine during ideal operation is. This is like relatively easier question. So the word turboshaft is just to make you confused, but we all know like all turbo jet engines or gas turbine engines, they work based on the Brayton cycle. In an ideal scenario, the ideal Brayton cycle works with isobaric combustion. So option B is correct. So the only exception in gas turbine engines which uses isochoric combustion, that is a pulse jet engines, that works on a different principle, but it is still a research stage. It's not the technology has been demonstrated, but it's not being used, that kind of engine, pulse jet. So excluding that one, all other gas turbine engines works based on Brayton cycle with isobaric combustion, right? Okay, so now move on to the next question. That is, how does the specific thrust of a turbojet engine change for a given flight speed with increase in flight altitude? This is very interesting question, and it's not straightforward, first of all. So it needs bit of a analyzing the question carefully. Okay, so first we have to identify few keywords. So they're asking for a turbojet engine. That's the first keyword. The next one, which property they are asking, the specific thrust. That's the next keyword. And what are the constraints they are given while you are deciding how does this varies. The constraint they are given is for a given flight speed, not flight Mach number, for a given flight speed with increase in flight altitude. So this is very interesting, right? So there are 4 options given. So one increases monotonically, other option decreases monotonically, C remains constant, and D first increases and then decreases. So what do you think? So which of these options are correct? Okay, I'm seeing a mixed response. Someone is saying it increases monotonically. Somebody is saying it increases and then decreases. Okay, let us see how exactly it varies. Right. So during our class, like we have seen these graphs with optimization of turbojet engines, right? So the thrust versus flight Mach number. The other graph is a specific fuel consumption versus flight Mach number. Both of these graphs are useful to decide answer for this particular question. The first question says how the thrust actually varies with the flight Mach number. See here, only the flight Mach number is given here as a function, not the forward speed. The forward speed, how you can define the Mach number at the inlet is defined by the forward speed of the aircraft divided by the speed of the sound, local speed of sound, say gamma r ti. So taking gamma and r to be constant for air, as calorically perfect gas within the troposphere altitude. We know the turbojet operates only within the troposphere, so that's safe to assume. So Ci is constant as per this problem statement, but how does temperature varies in troposphere? When you go from sea level to a higher altitude, how does temperature varies? It decreases, right? So Ti decreases as we increase the as altitude increases. So that makes Mach number increase, right? If Ti decreasing, that means Mach number is going to increase. So that is the first outcome you are going to get. So how does Mach number varies? It increases. So now you see, as Mach number increases at any given altitude, how does the thrust varies? It almost decreases first and then increases, decreases first and then increases for given altitude. It's not for varying altitude, but the question is specific that for a given flight speed with increase in altitude. So we are not interested in at a given altitude. For a given altitude, if you want to comment on, you can say the specific thrust first decreases then increases. That is true, but it is not for a given altitude. It is for a different altitudes. Now you are increasing the altitude, but thrust we can easily see for a different altitude it decreases. But does the specific thrust also decreases? This is an interesting part. So see, so from specific fuel consumption graph, we can see that the specific fuel consumption for a given flight Mach number or whatever Mach number you take, right? So it decreases as we increase the flight altitude. So we are combining both together. So what we are going to do, how do we define a specific thrust? Specific thrust can be defined as mass flow rate of the fuel supplied to the thrust developed by the engine. So we are again making one more assumption that thrust is optimum. Okay, so we are not having over expansion and or under expansion. So given that turbojet works only with the converging nozzle, so we are assuming we are not going beyond the optimum expansion. So that like we can treat pressure thrust contribution is zero. So that makes our life easier to comment on this problem. Okay, so now this can be easily shown as, so fuel to air ratio divided by sorry, this is SFC, specific fuel consumption, as is defined. So SFC can be written as F divided by Fs. Fs is specific thrust, right? So now you see, we are again assuming mass flow rate of the fuel is not going to change. It is constant. Okay. But we know the thrust actually going to decrease as we move with the altitude. So if mass flow rate of the fuel is constant, then what happens to F? That is, so we will rewrite it for specific thrust, that is going to be F divided by SFC. And we know if we increase the altitude, the denominator going to decrease because as we increase the altitude, SFC decreases. So this part is fixed, it decreases. But what about F? So F is defined as mass flow rate of the fuel to mass flow rate of the air. So we know, we are assuming that we are not changing the mass flow rate of the fuel to the engine. So we are assuming it to be a constant. So now we have to look at the variable mass flow rate of air. So how do we define the mass flow rate of air? That is density, incoming air velocity Ci, or the forward speed, and the inlet area. So we can calculate mass flow rate in this manner. And in the problem, it is given that it is constant, right? Also it is given that the same turbojet engine, so I can safely take inlet area to be constant. So the only parameter which varies is density. As we move the higher altitude, how does the density changes? Density decreases, right? As such increases. So if density is decreasing, other two parameters are constant, then mass flow rate of air is going to decrease as we move the higher altitude. So if mass flow rate of the air is decreasing, that means fuel to air ratio is increasing. So if fuel to air ratio is increasing and SFC is decreasing, what happens to my specific thrust now? The net result is Fs is going to increases monotonically, right? Yes or no? So now which option has to be kept as the final answer? Option A, right? It increases monotonically. Yes. So Anish has a question. Isn't it opposite? Can you specify it? Which relation you are saying, like which has to be opposite in nature? Yeah, SFC is correct, right? It's a mass flow rate of fuel to the thrust produced by the engine. Okay, like I want to stress out here. See, this is not defined for a unit thrust. Okay, don't take this definition is defined for a unit thrust. No, the amount of fuel you are um, supplying to the amount of thrust you are produced. So that is how you are defining. It is not defined for a unit thrust. Okay, it is defined for the actual thrust and actual fuel you supply. Okay, so this has to be cleared. So you don't take that wrong message. It's defined for unit thrust. No. Okay. So then we will move on to the next question. Again, this is based on the optimization graph. So they really tested your understanding of the topic, the optimization. We will see. How does the propulsion efficiency of a turbofan engine operating at a given Mach number and a given altitude change with increase in compressor pressure ratio? It's a very beautiful question. So see, the major keyword we have to look here, what they are actually asking, the propulsive efficiency. It's very important. The propulsive efficiency of a turbofan engine again. Okay. Now operating at a given Mach number, okay, and a given altitude change with increase in compressor pressure ratio. So if I increase the compressor pressure ratio, how does it change? So there are 1 2 3 4 5 keywords. So as soon as you see this kind of question, you have to identify the keywords. So I'm taking alternative route to answer this one. Though I could have taken the turbofan engine, but the definition of propulsion efficiency becomes much more complicated for turbofan engine. I'm reducing my problem definition by turbofan to turbojet. Okay, so they both work in a similar fashion. So though the propulsive efficiency definition changes for turbofan engine, but still it's a jet combined with the fan. So I'm just taking the turbojet engine because I want to see how the core engine part works with the given condition. So if I can comment on that one, so then the bypass part is we can easily take it. So it mainly depends on the turbojet performance overall. So we will see in that way. Okay. So now again, if you look at the optimization graphs, so we can have this kind of graphs: specific fuel consumption versus specific thrust, right? So why I need this graph? Because you see, whenever I define the propulsive efficiency for a turbojet engine, so it's usually defined as thrust power. See, it is a, so let me write it clearly. It is thrust power divided by the kinetic energy of the engine output. So I can write half m dot a cj square minus ci square. Okay, remember I am defining for a turbojet engine, but still we can comment for this particular question with this approach. Okay, so now the interesting part is, what is thrust power? Thrust power is nothing but thrust times the forward speed divided by half m dot a cj square minus ci square. So what is F divided by m dot a? F divided by m dot a is nothing but specific thrust, right? So 2 times specific thrust times ci divided by cj square minus ci square. So this is my propulsive efficiency. So let us keep this relation aside. Okay, so we will come back later. Okay, so now if you look at this equation, how specific thrust, sorry, this graph, how specific thrust varies. So that part we are first going to address. What are the constraints which is given in the question? The constraints they are given is like operating at a given Mach number. They are fixing the Mach number and the altitude. So those two variables it is fixed. So this graph is for a given Mach number and given altitude. So this part is fixed. So the first part we are actually taken care of. So we are fixing the Mach number and flight altitude. That is fixed. So the moment when you fix that one, then your forward speed is also fixed. Because for a given altitude, Ci can be written as Mach number times root of gamma RTI. So everything is fixed at the altitude, at a given altitude, Ti doesn't vary and Mach number is already fixed. So Ci is fixed. Okay. So now, what they're asking, if I change the compressor pressure ratio, so this is how the compressor pressure ratio, which is increasing. See, it is increasing, right? So, but now you look at this graph is not just the compressor pressure ratio as one of the variable, or only the variable. There are other variables too. There is a turbine inlet temperature. There is a specific fuel consumption. There is no statement is given about these two variables. They are not specified whether it is fixed or whether it is changing. See, like if I make an assumption that my specific fuel consumption doesn't varies, then I can draw a const line. So how does now specific thrust varies? So you see this point, this point, this point, and this point. So now clearly my compressor pressure ratio is increasing on a constant SFC line, and as it is increasing, you will come to a conclusion that specific thrust is also increasing. But that is a wrong conclusion because it is not given that SFC is constant. So I cannot make a statement just by using that. And if you take a turbine in the temperature is fixed, then again you will see that my SFC is going to increase first and then going to decrease. So that in that sense also it doesn't make sense because this constraint is not given to you. You cannot make that assumption now. Turbine inlet temperature is constant. All you have to see how these variables actually vary. So first we will see about a specific fuel consumption. So the specific fuel consumption can be again defined as F divided by Fs, right? Or Fs can be written as F divided by SFC. So whatever way we want to define. So let me move on to the next stage. Next slide. Okay. And how F is dependent F is defined as mass flow rate of fuel to mass flow rate of air. And how mass flow rate of air is related? So again, rho Ci AI. So mass flow rate of air is not going to change because it's at a given altitude and a given flight speed. This we already seen. If Mach number is fixed and altitude is fixed, so my forward speed is not going to change and engine inlet area is not going to change. So we are not changing the geometry at all. So these two variables are fixed and altitude is already fixed. So the density is also not going to change. So mass flow rate remains constant, is going to be constant for a given problem statement. So this part we cleared. So if I treat, I'm not changing the assumption, I'm making an assumption or else I cannot proceed. So I'm assuming m dot f is constant. So I'm not changing the fuel flow rate. So now my f is going to be constant. Right? So this part we addressed first. So now what about turbine inlet temperature? If F is constant, then I can easily use this idea how SFC varies. SFC is F divided by Fs. So it is only dependent on Fs. So I have to see how Fs is varying. If I can see how Fs is varying, I can easily come out on SFC. So that is fine. So now we see how turbine inlet temperature T03 varies. This question we will address. Okay, so we address for F. So now I am going to address for T03. How does it varies? So if you remember our discussion on polytropic process, so we can assume this compression process to be some kind of a polytropic process. So say I have a given pressure ratio across the compressor. So I can write for a change in temperature across the compressor as the pressure ratio to the power of gamma minus 1 divided by gamma times eta infinity C. So again, I am making one more assumption that change into the different color here. I am making one more assumption that the polytropic efficiency of the compression is constant for all pressure ratios, whatever we are going to investigate. Okay, so this is again the other assumption I am actually making. Okay, so keeping that in mind, if pressure ratio is increasing as per the given statement, so and T01 is not going to change because atmospheric condition is not going to change and I am not changing the inlet also. Ci is also not changing. So it is not going to change. So now how exactly T02 varies? If P pressure ratio increases in a compressor, what happens to T02? T02 increases, right? As pressure ratio of the compressor increases, right? So if T02 is increasing, now look at combustion process. Mass flow rate of the fuel is not changing and you are not changing the fuel also, the type of fuel. So I can write the energy balance within the combustion chamber. Let's put like this. So energy balance in the combustion chamber, I can write T03 is equal to T02 plus some terms which comes with the mass flow rate of gas and Cp of gas and those terms. So that is dividing over here. And some here again Cp of air divided by Cp of gas is there. All those terms I am not considering. I am treating they are all constants. They are not changing. So times I can get something like mass flow rate of fuel or F in terms of combustion efficiency times, or we will treating 100% efficiency, that is fine, QCV, right? So this part is not going to change, right? This we can treat it as a not a variable quantity for a given problem. So the only thing which changes here is T02, and we saw that T02 increases for increasing pressure ratio. If T02 is increasing, what happens to T naught 3? So it's addition of some constant. So T naught 3 is also increasing, right? As per the given problem statement, T naught 3 increases as compressor pressure ratio increases. So now we actually got into the conclusion that T naught 3 is increasing, and now we have to comment on what is a specific fuel consumption is like how the specific fuel consumption is behaving. If we can address that part, so our job is done. Yes. So because we saw that T naught 3 is increasing. So T naught 3 is increasing. If T naught 3 is increasing, what's happening to my Fs? Fs is also increasing. If Fs is also increasing, T naught 3 is also increasing, my SFC start increasing due to increasing T naught 3, and Fs is increasing again due to increasing T naught 3, right? So that is one part. But Fs can also decrease if the SFC is decreasing. So that is also happening. Why? Because if you see SFC, that is F divided by Fs. If Fs starts to increase, then SFC start to decrease at a given condition, right? So you see, if F is fixed, if Fs is increasing, then SFC is actually decreasing. See, like, so draw one constant line. What is happening? So SFC is decreasing, right? At a constant specific thrust. So there is a two-way this problem can be seen. So there is some part of the process where you can see the increase in Fs. Some part of the problem you can see the decrease in SFs, either due to the decrease in SFC or due to increase in T naught 3. So it can happen. So there should be a nice balance between those two to comment on that. So you know our propulsive efficiency is strongly dependent on Fs. So there is a part of the process for some combination of compressor pressure ratio and T naught 3, so that the specific thrust is decreasing, and some part of the process where the some combination of compressor pressure ratio and T naught 3, the specific thrust is increasing. So there is a nice interplay between them. So the best answer to this one is it decreases and then increases. So there is one possible answer which says both the options, decreasing and increasing nature. So this can be a better option among the given options. So everybody clear with this? Yes. So these are like a very intriguing questions, and it needs a lot of thought process. Okay. So in gate kind of environment, I would suggest keep these questions at the end. Don't try to answer in the first go, because this is multiple choice question. You have a better probability that you might lose a mark if you're not thought this question carefully. If you just pick something you think as a guess or those things, so you might lose a marks by picking the wrong answer. So you have to think carefully to answer these questions. So keep these questions at the end. Though it is 1 mark question or something like that, it looks a very straightforward by reading the question, but it is not. Okay. So these kind of questions are tricky. Okay, so let us move on to the next question. The shape of a supersonic diffuser that slows down a supersonic flow to a subsonic flow is. It should be very straightforward question. So what you have you should have a supersonic diffuser that brings down the supersonic flow at the inlet to a subsonic flow at the outlet. So what should this shape? So it has to be converging and diverging, right? So we have this nice area Mach number relation that guides us, like dA by A is equal to m square minus 1 times du by u for 1D quasi one dimensional flow. So with that, like, we can comment on what should be the shape for a supersonic diffuser. And once it reaches the minimum area, we know like the flow becomes choked. Then it has to still decrease to a subsonic value. So then you have to have a diverging area. So converging and diverging portion we need. Like, there's a theoretical one. The practical diffusers would look something like this. Some constant area duct, the throat, like this. But in any way, it's a converging, diverging duct. Okay. So move to the next question. An aircraft with a turbojet engine is flying at 270 meters per second. The enthalpy of the incoming air at the intake is 260 kilojoules per kg, and the enthalpy of the exhaust gases at the nozzle exit is 912 kilojoules per kg. The ratio of mass flow rates of the fuel and air is equal to 0.019. The chemical energy or the heating value of the fuel is 44.5 megajoules per kg, and the combustion process is ideal. The total loss of heat from the engine to the ambient is 25 kilojoule per kg of the air. The velocity of the exhaust jet is in meter per second. So this question is really a beautiful question. I can say by looking at this question, you might feel that it's a very complicated question because so many information is given, and it looks like a kind of entire cycle analysis question, because from inlet to outlet, heat addition and heat rejection, so many information is given to you. But you have to take a brief moment by reading the question very carefully. If you look at this question carefully, you will realize that it is nothing but a simple control volume approach. Though it is related to a turbojet as an engine, but you really don't have to dig into deep of the individual components of the turbojet engine. You are not going to analyze the compressor, you are not going to analyze the turbine, you are not going to analyze in the intake, you are not going to analyze in the nozzle or even the combustion chamber. You are not going to analyze any of the components of turbojet engine. You are just analyzing what comes in, what goes out. That's what given in the question. You see, flying at 270 meter per second, that's the inlet condition. The enthalpy of the incoming air, that's the inlet condition, or at the intake. So the inlet condition again, what comes in. And enthalpy of the exhaust gases at the nozzle exit, it's the outgoing condition or the outlet condition. So what comes into the control surface and what goes out of the control surface, that information is given. The ratio of the flow rates of the fuel and air is equal to 0.019. Again, the mass of the fuel which is coming into the control volume, that information is given, and the energy which brings in to the system, that is given along with that. Again, it's what's coming into the control volume. And combustion process that asked you to treat ideal, so you don't have to worry about the combustion efficiency and all. So the total loss of the heat from the engine is given. Again, it is the what goes out of the system. So if I draw the, and one more thing you have to notice here while taking this information is it is given per kg of air. So it is given with respect to the mass flow rate of air. So that part you have to consider. It's not given for mass flow rate of gas. Just for mass flow rate of air it is given. So that is one more information you have to be very much careful about. Okay, so now you see, so if I draw the simple control volume enclosing entire turbojet within the control volume, what do I have? So what's coming in, what's going out, that's it. So they are given the enthalpy at the inlet and enthalpy at the outlet, the heat addition. They are given in the information where you can easily calculate the heat addition. They are given F and calorific value of the fuel. So from here you can calculate the Q in and what is going out of the system, Q out. The simple model is sufficient to answer this question. Now we will see how we can address this question. Okay, so incoming air velocity is also given. So the best approach for this one is to apply the steady flow energy equation, right? The first law applied to a flow process. So we know that the energy or the conservation of energy has to be maintained. So what does our first law of thermodynamics says us? Sorry. So if I apply the conservation of energy to the, it is H1 is given. So you can calculate H01, that is fine. Here also H2 is given. And they are asked you to calculate what is the exhaust velocity of the nozzle. That is fine. So the conservation of energy says us is just dq is equal to the change in internal energy of the system plus the work done, external work done, right? So not dq, delta q, right? So if I apply that one to a flow process, it can be shown that mass flow rate of air times h1, the enthalpy, it's a specific enthalpy multiplied with mass flow rate of air plus again mass flow rate of air times the kinetic energy at the inlet Ci squared divided by 2 plus mass flow rate of the air times the heat addition this is not exactly mass flow rate of the air, it's mass flow rate of the fuel times heat addition, that is the energy you are adding in, and with combustion efficiency if it is there, plus what is the heat which is going to reject it, it is the combination of total heat change, right, delta q across the system boundary. So it is the mass flow rate of the air times q out, because q out is given in terms of the per mass flow rate of air, so I am just multiplying the mass flow rate of air to be consistent with the units. Okay, so which is equal to the right hand side, that is mass flow rate of the gas. So the moment when you add the mass flow rate of fuel, so now the continuity will tell you the mass flow rate of gas should be equal to mass flow rate of air plus mass flow rate of fuel. So there is addition of mass to the system, so we have to take care of that. So it is mass flow rate of gas times H2 plus mass flow rate of gas times Cj square divided by 2 plus if there is some work transfer, right? Any external work transfer. But for the given question, we don't have any external work transfer, so we can easily neglect this part to be 0. All we have is this part now. So now you see, if I take mass flow rate of air common here, it becomes 1 plus mass flow rate of fuel by mass flow rate of air, that is 1 plus F, right? So I can take mass flow rate of air common from the equation over here. So that makes it 1 plus F times H2 plus Cj square divided by 2, right hand side. The left hand side, again, if I take mass flow rate of air common, this is H1 plus Ci square divided by 2. This is mass flow rate of gas, so it becomes 1 plus F times what is Q in. I can easily write it as, sorry, it is just mass flow rate of fuel. So just F times QCV, that is the heat input, times the combustion efficiency, minus mass flow rate of air is taken common, so it is just Q out, right? So now I have a nice balance, so it is 100%, so I can treat it as 1. So now I can cancel out mass flow rate of air and mass flow rate of air from both LHS and RHS. Now you see all the information is given in the problem except Cj. So that is what you are calculating. So write this equation in terms of Cj. So how does it look like? It becomes 1 divided by 1 plus F multiplied with H1 plus Ci square divided by 2 plus F into QCV minus Q out minus H2 is equal to Cj square by 2, right? So now multiply 2 to this side and take a square root. So if you put all the numbers, so you should be able to get Cj is equal to something around 606.834 meter per second. So what is asked in the question, you have to keep it into 2 decimal places and round off. So if you round off to 2 decimal places, it becomes 606.83 meter per second. So clear? Okay, so let us move on to the next question. A twin spool turbofan engine is operated at sea level with conditions are given. TA is equal to 1 bar, TA is 288 Kelvin. The engine has separate cold and hot nozzles. During the static thrust test at sea level, the overall mass flow rate of air through the engine and the cold exhaust temperature are measured to be 100 kgs per second and 288 Kelvin respectively. The parameters for the engine are fan pressure ratio is 1.6, overall pressure ratio is 20, bypass ratio 3.0, turbine entry temperature 1800 Kelvin. The specific heat at constant pressure Cp is 1005 joules per kg Kelvin, and the ratio of specific heat, that is gamma, is 1.4 for the air. Assuming ideal fan and ideal expansion in the nozzle, the sea level static thrust from the cold nozzle is, and again in kilonewtons we have to put, and answer we have to keep in 2 decimal places by rounding off. Okay, again if you look at this question, it looks very lengthy question because the information given here is so much, but you have to take a moment and read the question carefully and what is asked in the question carefully. So all they are asking is to calculate for the cold nozzle alone. So the moment when you have to calculate for the cold nozzle alone, so this information is irrelevant. This information is irrelevant. We don't really have to worry for that one, right? And again, the very important key word we have to see here is the static thrust. What do we mean by a static thrust? Static thrust is nothing but when the engine is not moving, so there is no forward speed. So the forward speed of an engine is 0. So that is the static thrust, right? So now we are reduced our problem because it's a static thrust condition. And by looking at this question carefully, because we are asked only to calculate for cold nozzle, so we again reduced our problem and we straight away omitted whatever it is not relevant for the given problem. So again the problem become simple. So now again there is a one more information. The moment when you read this statement in the beginning, you will uh, you think it's going to be a tougher question. No, the twin spool. The twin spool has nothing to do with the calculation, whatever you are going to carry now. Because the twin spool, they are just given to confuse you. It really doesn't come into picture when you're calculating the asked information, right? So now it is a turbofan engine. So let us take the relevant variables with us. So this is relevant information, the sea level conditions, and overall mass flow rate, which is important. This is mass flow rate of the air which is coming in, and the cold exhaust temperature. So this is the temperature at the exit plane of the cold nozzle. This is important. And fan pressure ratio, which is important, and bypass ratio, which is important. So let me call it as pi f, and this is beta as bypass ratio, and this is important information. And other important information is this one, the assumption they asked you to take: ideal fan and ideal expansion in the nozzle. So I can straight away say that the efficiency of the fan is going to be 100%, efficiency of the nozzle is 100%. So and both of them are operating in isentropic conditions. So that part is clear now. So now let us move on to calculate the asked information. So they are asked you to calculate the cold thrust. We know for a turbofan engine. So if I draw a simple schematic, so I have a core engine and I have a bypass. So I really don't care what happens in the core of the engine. So all I am interested in what is happening in the bypass duct, right? So I have a information over here, PA. So see here, my stagnation condition in the inlet is also equal to static condition because Ci is 0. So I can easily take T naught A is equal to TA, P naught A is equal to PA, assuming steady flow. Okay, so it really doesn't matter because it's a stagnant condition anyhow. And mass flow rate of the air is 100 kgs per second. So from the bypass ratio, so I can easily say that mass flow rate of air can be written as mass flow rate of the air which is going into the core of the engine or the cold nozzle plus mass flow rate of hot, that is which is going into the engine. So from here I can use the definition of beta, so that is bypass ratio. How do we define bypass ratio? That is mass flow rate of cold air to mass flow rate of hot air. So if I use that one, so I can show that mass flow rate of cold air can be written as beta times mass flow rate of the air divided by beta plus 1. So you just take the mass flow rate of cold air common over here. It becomes 1 plus 1 divided by beta. So let me do that step. So becomes 1 plus mass flow rate of hot air by mass flow rate of cold air. That is 1 divided by beta. So keep this on the right hand side. So mass flow rate of cold air is equal to mass flow rate of air times. So if you take to the other side, it becomes 1 divided by 1 plus 1 by beta. So if you take the LCM, it becomes beta plus 1 and divided by beta. So beta goes to other side. So it becomes beta times mass flow rate of air divided by 1 plus beta. So that is what we have written here. Okay, so that part is fine. So beta is given. So we will calculate the mass flow rate of cold air. That is nothing but That's nothing but 3 into mass flow rate of air is 100 divided by 3 plus 1, that is 4. So it's going to be 4 ones are 425. So 25 into 3, that is 75 kgs per second. That is my mass flow rate of the air which is going in the bypass duct. So that part we got. So now to calculate P naught 1, that is like if I say this is stage at the atmospheric condition, immediately after the fan, this is the state 1. The at the nozzle exit, I will call the state 3. Okay. So now I have to calculate the information over here to know the thrust, because I have to calculate how the flow is expanding from what pressure to ambient condition. So for that one, so I want to calculate P naught 1. So how can we calculate P naught 1? So P naught 1 is nothing but fan pressure ratio times the P naught A. Why? Because we don't have to worry about the efficiency of the fan now, because it is given, it's working ideally. So I can easily calculate P naught 1 as from the given information. So this is 1.6 times P naught A. P naught A is 1 bar. So it is going to be 1.6 bar. That is P naught 1. So this one we calculated. Once I know the P naught 1, how I can calculate T naught 1? So T naught 1 can be calculated as T naught A times pi f to the power of gamma minus 1 by gamma. Because it's a isentropic process, ideal fan. So T naught A is 288 Kelvin. So 288 times pi f is 1.6, gamma minus 1, that is 0.4 divided by 1.4. So this becomes 329.4 Kelvin. So we calculated T naught 1. So now to calculate the cold thrust, how we can calculate the cold thrust? Cold thrust is nothing but mass flow rate of the cold air times the velocity at the cold nozzle, right? Cj, the jet exhaust velocity at the cold nozzle, minus mass flow rate of air times Ci. That we are really not worried, because Ci itself is 0. So inlet momentum drag is nullified. So only part we have to calculate is this one. And what assumption we are making? It is optimally expanding. So all we need to calculate now is this quantity, the cold exhaust jet velocity. So now we will see how we can calculate that one. So again, I am using the energy equation. So because nozzle is ideal, so T naught 1 is equal to T naught at the exit plane. That can be written as Te at the exit plane times Cj of the cold air at the exit plane of the nozzle divided by 2Cp. So I am using the energy balance. So from here, I can write for a Cjc equal to square root of 2Cp times T naught E minus Te. So actually you can directly calculate from here, because T naught E is equal to T naught 1 that you already calculated, and Te is already given in the problem. So nozzle exit plane temperature is given as 288 Kelvin. So it is already given in the problem. So you can directly use that one, or you can also go and do one more step, that is taking T naught T out common, it becomes 1 minus Pe divided by P naught T to the power of gamma minus 1 by gamma. This way also you can approach, because Pe is known. Assuming it is optimally expanding, Pe is equal to Pa. Pa is given in the problem, 288, 1 bar. So P naught is, you calculated 1.6 bar. So you can use this approach, or T naught and Te you can directly use from your calculation and given condition. So in both the way, you should be able to get cold nozzle exhaust velocity is 288.44 meter per second. Cp is given in the problem, so you can use that. So now you can calculate the cold thrust equal to m dot cold air or bypass mass flow rate times the jet exhaust velocity in the cold nozzle. It is going to be 21.633 kilonewton. So look at the question again. Round off to 2 decimal places. So just keep 21.63 kilonewton. So clear?
Sir, can I go to the next page, sir? Just a minute.
Yes.
Sir, no, previous ones.
Okay. Yes, Ashish. If a overall pressure ratio is given and the fan pressure ratio is given, so the fan pressure ratio is the pressure rise which happens across the fan. That is a fan pressure ratio. The overall pressure ratio, whatever they are given, that is for the compressor stages. So you can have a multiple stage compressors. So the overall compressor pressure ratio is called as overall pressure ratio, sometimes OPR. That is how they will mention. Okay. So if you want to calculate the work done by the fan, so then you only have to use the fan pressure ratio, not this overall pressure ratio. If you want to calculate work done by the compressor alone, then you use only overall pressure ratio. Don't include this one. If you want to calculate the overall work delivered by the turbine, then you will add both. If in the case turbine is running both. If it is a twin spool configuration as stated in the problem, then what you do, you match the work done appropriately. Which turbine is running the compressor, you will match that part, and other part of the turbine which is running the fan, you will match that one. So that can also be done. So you have to do the matching appropriately. Okay. And why do you have to divide the overall pressure ratio by fan pressure ratio? It has nothing to do with that. You don't confuse it, that one. When you do this dividing pressure ratios and all, when you have identical stages of a compressors, then if the overall pressure ratio is given to you, then to calculate the individual stage pressure ratio, then you have this idea of dividing them, right? So this we discussed in the class, like, so if I have overall pressure ratio given to me, so that is nothing but P naught of the nth stage to P naught of the first stage. So then I can write like P naught n divided by P naught n minus 1 multiplied with P naught n minus 1 divided by P naught n minus 2. So multiplied to P naught 2 divided by P naught 1 is first stage. So like that you can make it. So or else you can write like multiplication of I is equal to 1 stage to n stage P naught I divided by P naught I minus 1. Like that you can take, provided every stage is identical and has the same work done. So this is very special case, the special assumption you have to make. Okay. So that is where this multiplication idea comes. This relation is general. P naught n by P naught, it is general. It doesn't matter. But you can write only in this way. This is also fine. But if you want to write it to be equal to P naught 2 by P naught 1 to the power of n number of stages, this index you can keep only when every single stage is working identically. And delivering the same work done and same pressure ratio is happening across the individual stages. Then only you can use that. Okay. Ashish, your question is much more specific. The question itself is saying the overall pressure ratio across fan and compressor. They are already combined that pressure ratio by stating it. Then you have to consider in such a way that you have to divide both of them. How much of the fan pressure ratio is there and how much of compressor pressure. The statement itself is given in that sense. It is combined. Then you have to do like that. You have to take out the fan pressure ratio from that one and keep the other part of the pressure ratio as compressor pressure ratio. This is a very different question. It is not general statement. It's just specific to that question. Okay. Okay, let us move on to the next question. At the design conditions, the velocity triangles at the mean radius of a single stage axial compressor is such that the blade angle at the rotor exit. Yes, Harini, you raised your hand. You have any question? Okay. So at the design conditions, the velocity triangle at the mean radius of a single stage axial compressor is such that the blade angle at the rotor exit is equal to 30 degree. The absolute velocities at the rotor inlet and the exit are equal to 140 meter per second and 240 meter per second respectively. The flow velocities relative to the rotor at the inlet and the exit of a rotor are equal to 240 meter per second and 140 meter per second respectively. The blade speed u at the mean radius of the rotor is. Again, the statements are lengthier, but the problem is simpler. So you see here, what they have given is the 50% reaction stage triangle. They are given at the mean radius. So that's the first condition we satisfied. And then they are given that absolute velocity at the rotor inlet, right? They are given C1 and C2 as 140 meter per second and 240 meters per second. Also, they are given flow velocities relative to the rotor, that is W1 and W2 at the inlet and exit. So W1 is given, W2 is also given. So you see here from the given information, C1 is equal to 140 in meter per second, C2 is equal to 240. Similarly, W1 is equal to 240 and W2 is equal to 140. So if I treat CA to be same, then this velocity triangle becomes identical or symmetric. So because U is the common velocity component for both the velocity triangles. So for a given CA which is constant in a given stage, then this velocity triangle is symmetrical. So that means the degree of reaction is going to be 0.5. So that information is hidden within the statements, but you can recognize it. So my problem is like largely reduced because of the given statement. Right? So now we see how we can solve this question, because like they are asking you to calculate the blade speed u. So to calculate blade speed u, what are the approaches you can get? So you can be either written as CT1 plus WT1, or you can also write u is equal to CT2 plus WT2. What is CT and WT? That is the tangential component of relative velocity and absolute velocity vectors. So either from inlet triangle or from the outlet triangle you can calculate. So the also the information is given what is beta 2 within the velocity triangle. They are given what is beta 2. So I have beta 2. So I know beta 2 is nothing but 30 degree, and I know W1 is nothing but, sorry, W2 is nothing but uh, 140, right? Yes, W2 is nothing but 140 meter per second. So if I use this information, see for that velocity triangle alone, I have CA, I have W2, I have WT2, so I have beta 2. So from here, if I define the cosine cos beta 2, that is going to be CA divided by W2. If I define the tan, so that is going to be WT2 divided by CA, or if I define the sine, so that is going to be WT2 divided by W2. So from here I can calculate CA, I can also calculate WT2 from the given information. So if I use this relation, CA is going to be W2 cos beta 2. So then I get CA is equal to 140 into cos 30. Cos 30 is root 3 by 2. So that I will get. And if I again use the WT2 from here, so that is going to be WT2 is equal to W2 sine beta 2. So that is going to be 140 into sine 30 is 1 by 2. So it is going to be 70 meter per second. So I got what is WT2, I got what is CA. So now either I have to calculate what is CT2, then my job is done. So I can easily add these two to get the U. So now how I can calculate CT2? So if I look at the other part of the triangle, so that is, let me use a different color. Okay. So the other part of the triangle is C2, CA, CT2. So I have CA, I have CT2, I have C2, and this is unknown alpha 2. But now you see, I know what is CA is. But alpha 2, I don't know. But I can calculate alpha 2 because I know what is C2 is. So if I define the cos alpha 2 from this triangle, that is going to be CA divided by C2. So from here I can calculate alpha 2. So CA is this one, 140 times root 3 by 2. C2 is going to be 240. So if I use that one, so it is the cosine cos of alpha 2. So you take the cos inverse. So you get alpha 2 to be equal to nearly 60 degree. That is 59.66 degrees. So once I know alpha 2, now I can calculate CT2. So what is CT2? Or you can also use Pythagorean triplet. So you know CA, you know C2, you can easily calculate CT2 using Pythagorean triplets. So CT2 is going to be C2 sine alpha 2. So use that one, you get CT2 to be equal to 207.123 meter per second. So this is one approach, or else you can also calculate CT2 is equal to square root of C2 square minus CA square. That is also possible. You should be able to get the same answer. So now both CT2 is known, WT2 is known, WT2 is known. So add these two. So U is equal to CT2 plus WT2. So this is going to be 207.123 plus 70. So this is going to be 277.123 meter per second. And look at the question again. So they ask you to put in two decimal places by rounding off. So it is going to be 277.12 meter per second. So clear? Okay, so now move on to it's the last question from GATE 2021 on propulsion topic. A single stage axial turbine has a mean blade speed of 340 meter per second at the design condition, with blade angles at inlet and exit of the rotor being 21 degrees and 55 degrees respectively. The degree of reaction at the mean radius of the rotor is equal to 0.4. The annulus area at the rotor inlet is 0.08 meter square, and density of the gas at the rotor inlet is 0.9 kg per meter cube. The flow rate through the turbine at these conditions is, again in kgs per second, round off to a two decimal places. So this question is straightforward in a sense that all we have to understand, how do we calculate the mass flow rate, because they are asked you to calculate the flow rate, right? So how do we calculate the mass flow rate? So if you look at the Reynolds transport theorem carefully, so for any arbitrary volume, right? So if it is the surface through which a flux is going out, with the surface normal is given to be n vector, and some flux is going out, say velocity vector. So the flux is always going to be calculated with these vectors are having some angle, theta. So what is the projection of this vector onto the unit normal? So that is v dot en. So that is going to be cos theta, and n is being unit normal vector, so it's the magnitude is going to be 1, so it is going to be v cos theta. So this is the physical meaning of this dot product, is nothing but a flux, right? Whether it is going out or going in, depending on this whether velocity vector is outward or inward, or area vector is outward or inward. So based on that, like, you decide it. So either theta is going to be 180 degrees, or theta is going to be 0 degrees. Based on that, you have positive or negative sign, or based on the angle. So it can vary from 0 to 180 degree. That's it. Okay. So now this is the meaning of flux. So now if you look at the axial flow turbine or compressor, whatever, so I have a stage like this, right? So I'm simplifying the problem, right? So I have a shaft, right, which is running out, which is rotating, which is connected to a set of blades. Sorry, it's connected to a set of blades, right? So flow is entering at any angle with velocity vector c, absolute velocity vector, but the area is always pointing normal, the area normal vector. And if you look at this one, so it is at an angle theta. So if you say air angle, I will call alpha only. So I have a unit normal in this direction and flow velocity which is coming in this direction with some angle alpha. So then what is the projection of C onto this vector? So that is going to be C dot n. So that velocity vector is nothing but axial component of velocity. That is the part of the vector, right? C cos alpha. CA cos alpha. What is, sorry, C cos alpha. So if you look at the velocity triangle carefully, so you have C and you have alpha. So then what is the cosine of this one? So this is unknown. So you have C. So what is the cosine of this angle? So cos alpha is nothing but this unknown divided by C. So that is going to be C cos alpha. So C cos alpha is nothing but that unknown that we call it as axial velocity vector for axial flow machines, right? So this is the velocity component I have to consider for the calculation of mass flow rate, because that is mass flow rate is the flux which is going in or going out of the control volume or through the control surface, right? So that is the component of velocity we have to consider. So now we are clear with what velocity component we are interested in to calculate. So now if I want to calculate mass flow rate, that is going to be density, the component of velocity we are interested in, CA, times the annulus area. So this is, if I want to calculate the area through which the mass is going in or going out, the flux, so that area value is nothing but the annulus through which the flow is entering. So if I look at in the front view, so if I look at the stage from a front view, right? So this is again the shaft. So say this is D2 and this is the diameter 1. So the area through which mass is going is going to be pi d2 square minus d1 square divided by 4, right? This is the area. So this part is given in the problem. This is called annulus area. So that is already given in the problem. It is annulus area at the rotor inlet is 0.08 meter square. Also the density at the inlet is also given 0.9 kg per meter cube. So this is given in the problem. This is given in the problem. All I have to calculate is CA. So for that the information is given in the problem again. So let us try to find out that one. So now we got to know what we are going to calculate or how we are going to calculate. All we have to do now is to fill in the blank. What is missing, that we are going to calculate first. So I have a turbine inlet, turbine stage, right? So turbine stage always starts with the nozzle or the stator, which the flow is leaving the nozzle is absolute velocity vector C1, and then the rotor which receives the flow, right? So it is moving with the velocity, peripheral velocity u. So let me fill in that velocity vector here. That is going to be u, and because of the rotation, so we have to consider that the relative velocity at which the flow is actually entering the rotor stage, that is going to be w1. So now I can easily define the axial velocity component for C1 or for W1. So if I draw this velocity triangle bit more elaborately, So this is C1, W1. So or I can write for C2, W2 and all, because my entry velocity triangle is to the stage is at the nozzle entry. So it can be something like this: C1, alpha 1 and CA. It can come like this, with this is being CT, not U. Okay, so then this is going to be CA. So this angle is going to be alpha 2. This angle is going to be theta 2. This component is going to be U. So this has to satisfy the vector relation C is equal to U plus W. So now this component is going to be CT2 and this component is going to be WT2. So similarly at the exit of the rotor, so my velocity triangle something looks like this. So the relative to the blade, the velocity is W3, and I have again axial component, and there is a rotation, so that is U in this direction. So my C will be in this direction. So again it is going to satisfy U plus W equal to C. So now my alpha 3 is this one, beta 3 is this one. So now if I look at, so this is my WT3 component, this is my CT3 component. So if you look at carefully, so now U is nothing but WT3 minus CT3 over here, whereas for the inlet velocity triangle, U is nothing but CT2 minus WT2. So these are some part like you can analyze, but for the given problem, we only need to calculate CA. For that, we really don't have to look into all the trigonometric information about the triangle, since the question is asked. So I'm just refreshing what are the things we can see. But for the given problem, all we are interested in calculating the CA. So the degree of reaction is given to us in the problem. So that can be written as 5 by 2 times tan of beta 3 minus tan of beta 2. So in the problem, everything is given. Beta 3 is given, beta 2 is given, um, U is given, CA is unknown, you have to calculate, but R is given. So, and flow coefficient phi is nothing but CA by U. So I'm just substituting over here, that becomes 2R is equal to CA by U times tan beta 3 minus tan beta 2. So this, sorry, so this becomes 2UR divided by tan beta 3 minus tan beta 2 equal to CA. So now you put everything. U is 340 meter per second given in the problem. R is 0.4 given in the problem. Beta 3 is 55 degree given in the problem. Beta 2 is 21 degree given in the problem. So if you put this one, so you will get CA is equal to 260.465 meter per second. So you keep that back into the mass flow rate here. So you should be able to get mass flow rate is something around 18.75 kg per second. So How it is asked? Yeah, round off to 2 decimal places. So 18.75 kg per second. So clear, right? Yes. So now we'll move on to the final question. This is again interesting question. Airflow rate through the gas generator of a turboprop engine is 100 kgs per second. Stagnation temperature at the inlet and exit of the combustor are 600 Kelvin and 1200 Kelvin respectively. Satish, you have any questions? You raised your hand. Okay. The burner efficiency is 90% and the heating value of the fuel is 40 megajoules per kg. The specific heats at constant pressure CP for air and burn gases are 1000 joules per kg Kelvin and 1200 joules per kg Kelvin respectively. The flow rate of the fuel being used is what? That's the question in kgs per second, and again rounding off to 2 decimal places, and they are specifically stressing out that do not neglect the fuel rate with respect to the air flow rate. So they are asking don't neglect fuel to air ratio. So basically. So now this problem again we can simplify by using the control volume approach. Say I have a control volume enclosing a combustor. So I have inlet condition, I have outlet condition. So mass of the fuel which is coming in, which has a specific heating value of QCV that is given in the problem, 40 megajoules per kg of fuel. And the efficiency of the combustor is given to be 90%. So that is 0.9. And mass flow rate of air which is coming in is 100 kgs per second. And the temperature at the inlet is 600 Kelvin. It's a total temperature. And Cp for air which is coming in to the combustion or control volume is 1000 joules per kg Kelvin, and the temperature, stagnation temperature at the exit of the control volume is 1200 Kelvin. It rises to a temperature of 1200. So the gas has the property 1200 joules per kg Kelvin, specific heat of the gas at constant pressure. Mass flow rate of the fuel, which is unknown, we have to calculate what we are supplying here, right? So this is the simplified version of the problem. It's a control volume. So we know we can do a energy balance over here, steady flow energy equation. So since there is no work done is being added, or like work is being done on the system or by the system, so we can safely use the work done is absent. So that makes our energy equation simply a internal energy change is going to result in heat addition here. So we can equally write it is going to raise the enthalpy of the system. That's what happens here. So total enthalpy at the exit of the system is nothing but total enthalpy which is at the beginning of the uh, combustion operation, or which enters the system, plus the energy we are adding. to change the internal energy of the system. So that's what we are doing here. So now also we are neglecting the velocities which is coming in or going out. So we are treating it as like fairly low speed, so we can neglect the effect of velocity change. So now it is going to be mass flow rate of gas times Cp of gas. How we are just defining the enthalpy here. T03 equal to mass flow rate of air times Cp of air times T02 plus the energy addition, that is going to be mass of the fuel you are adding and the heating value of the fuel which the fuel is consisting, and out of which how much you can actually add as an energy, that is given by the efficiency. So eta B times heating value of the fuel. So this is the energy the fuel carries, out of which you are only able to use the 90% of that one to add as a energy or raise the enthalpy of the system. So now this system is clear to us. All we are going to do now is the continuity will suggest us the mass of the gas which is leaving out of the system equal to mass of the air which is coming into the system plus mass of the fuel which is coming into the system. So the net mass flow rate has to be maintained. So it's a continuity. So from here I can write in this way. So I can write mass of the gas as mass of the air plus mass of the fuel times Cp of gas times T03, which is equal to mass flow rate of air times Cp of air times T02 plus mass flow rate of fuel times eta B times QCV. So now if I take mass flow rate of air common over here, so that becomes 1 plus F, that is, what is F? F is mass flow rate of fuel divided by mass flow rate of air times Cp of gas times T03 equal to mass flow rate of air times Cp of air times T02 plus again mass flow rate of fuel to mass flow rate of air, that is going to be F times eta B times QCV. So I can cancel this and this from both the side. So now you write it for just F. So if you write it for just F, so that is going to be CPG T03 minus Cp of air times T02 divided by eta B times QCV minus Cp of gas times T03. So now you can calculate what is F. So it is because everything else is given to us. So you can write F as mass flow rate of fuel by mass flow rate of air, which is equal to this one, Cp of gas T03, that is 1200 into 1200. This is joules per kg Kelvin. This is Kelvin. It is going to be joules per kg minus Cp of air is 1000 times T02 is 600. Again, joules per kg Kelvin. Kelvin. The Kelvin get cancelled. It remains in joules per Kelvin kg. So again, 0.9 has no unit. It has unit 40 times megajoules 10 to the power of 6 joules per kg. It's already in the consistent unit what we are getting here. And this one 1200 times 1200. So now you will get something around fuel to air ratio as 0.024305. So I am just keeping many digits. You can just keep just to the third digit. It is fine. So that is equal to mass flow rate of fuel divided by mass flow rate of air. So mass flow rate of air is already given in the problem, that is 100 kgs per second. So you multiply that one 5 into 100. So that is going to be 2.4305 kgs per second of fuel flow rate. Right? So now look back the question. They are asked you to keep in two decimal places by rounding off. So it is going to be 2.43 kgs per second. It's fine. So everybody clear, right? Yes. So that ends our discussion on gate propulsion questions from 2021 paper. You guys have any doubt? I can take area ratio and optimum area ratio. What is the difference and how? Okay, this is slightly a different aspect from what we are discussing here, but still I can take. So Vasant is asking a doubt on area ratio and optimum area ratio and what is the difference and how it says like under expanded or over expanded. So see, this question has to be specific. So I am assuming your question is from the CD nozzle perspective, because if you are considering only a convergent nozzle, then the over expanded and under expanded and those three conditions will not be there. There will be only two conditions. Either it is optimum expanded or it's going to be an over expanded. So that is convergent nozzle. For the convergent divergent nozzle, all these three conditions can be possible. So you see, so take any CD nozzle. Okay, so I have a throat area 80 and I have a exit area. So this area ratio, what we call is the ratio of AE divided by AT as a parameter epsilon or something like that is called area ratio. So now based on this area ratio, whether it is greater than the design condition or less than the design condition, we can say whether the nozzle is operating over expanded way or under expanded way. So the important point here is area ratio is much more general. It is specific to a nozzle geometry. It doesn't care whether the nozzle is operating over expanded way or under expanded. It's the given nozzle has this specific geometry. It is given by this area ratio. Okay. And optimum area ratio is that area ratio for which flow is expanding optimally. That is an optimum. So when epsilon matches with the optimum expansion, then that area ratio you call it as optimum area ratio. Now you compare with that optimum area ratio. Optimum area ratio is what you want to design. So that is the desirable design condition. So now you compare for a certain area ratio, you have an optimum flow. Say that is your reference now. Now you see what happens if I decrease my area ratio from that optimum condition. So you have some exit pressure which is matching with your ambient pressure or the back pressure. Okay, so that is an optimum area ratio. So I call it as epsilon opt. Okay, so now you decrease your area ratio less than that optimum area ratio. Still you have the same back pressure, but your exit plane pressure is not going to be same because you changed your nozzle geometry. The expansion is different, right? Yes. So now you can have another condition, that is if area ratio is greater, like you increased your area ratio than the optimum area ratio. So now you have to see from the gas dynamic perspective, keeping the throat area same, you are just increasing or decreasing the exit area. So like say for this condition, you are decreasing the exit area from the optimum condition. For this one, you are increasing the exit area from the optimum condition. So keeping all other variables, P naught, T naught, whatever it is there at the upstream, you are not changing. So you are not changing this area ratio either. So you are not changing the throat area first. So you are just fixing that one. So now your flow is going to be choked for certain pressure P0 and T0 and for a given area of the throat. So it is always going to be choked. So that is your first assumption you are making to proceed. So now for increasing the area or decreasing the area, how does this the flow in the downstream of the nozzle is going to change? So you can always use this isentropic relation, right? So area at any two station, so ax by ay can be written in terms of my by mx times square root of 1 plus gamma minus 1 by 2 times mx square divided by 1 plus gamma minus 1 by 2 times my square whole to the power of gamma plus 1 divided by gamma minus 1. So this relation you can easily show from mass flow balance. So that is like mass flow rate is constant. So from there, so put one of this area to be throat. So that is going to be AE divided by AT. So replace Y by throat. So that's My is going to be 1 because throat you are seeing choked condition, and it is going to be exit plane Mach number times again 1 plus gamma minus 1 by 2 times me square divided by it is going to be 1. So it is you are going to see gamma plus 1 divided by 2. So whole to the power of gamma plus 1 divided by gamma minus 1. So now from here you can calculate what will be your Mach number. So this is bit a complicated process because it's not straightforward relation, but still you can get the what would be your Mach number if you change the area ratio. So from here you can actually see whether you are going to get an increased Mach number or decreased Mach number than the required. So this is again considering optimally expanding. Okay, so the moment when you are changing the area ratio differently and your flow condition at the back is not changed, so then you can actually have a under expansion or over expansion. So I think like this part I discussed in length during our rocket propulsion course. You guys can go back and check again. I am actually giving it to you as an assignment to you, so you have to refresh that memory back. Also it is explained in our material, you can see there. Okay, I'm just giving the hint or the approach through which you can comment on these kind of questions. I'm just leaving over there because it's really not a part of the discussion what we are doing so far. Okay, okay then, so if you guys have any no other questions, so we will wind up over here. So thank you for attending. Okay. Yeah, sure.